Good afternoon, everyone, and welcome to today's BHS webinar on continuous simulation modeling, a review and practical application. So we are joined today by Claire Samuel from Jacobs, Paul Wass from JBA, and Donna Wilson from the Environment Agency. And they're going to be sharing some recent work that they have done on continuous simulation modeling. But before we get into that, I've got, as usual, some housekeeping points to make. So please make sure your microphone is switched off and your video is switched off for the duration of the webinar. The meeting will be recorded and it will be uploaded to our YouTube channel in the near future. We do appreciate that we've been having some problems with our YouTube channel recently, and we do have a bit of a backlog. Please bear with us. We are making our way through those, and these videos will be up on our YouTube website as soon as possible. We do expect quite a few people today, so rather than you raising your virtual hand, if you have any questions, then please do put them in the text box, in the chat box, and Kirsty will be going through those at the end of the session and relaying them to our speakers. Just a quick plug on the BHS. The BHS is run by volunteers. So if you're interested in helping out, then please do get in touch. We do generally encourage interest and scholarship, good practice within the hydrology community. We run in-person events and webinars such as these. Our membership is very cheap, only £30 a year, and you do get a lot of benefits with that. You get a very good newsletter, and you do get discounts on our in-person meetings as well. So it is well worth signing up to. Speaking of in-person meetings, we have our annual symposium on the 23rd and 24th of September, which is our yearly event where all hydrological community comes together and shares experiences, networks, and catches up with each other. So if you're interested in that, please do have a look at our LinkedIn site. Or if you're on the mailing list, have a look at the mailing list. I will also post some links to this event in the chat for this. We are also accepting abstracts. So if you would like to come and present either a poster or a presentation, please do get in touch. Abstract deadlines are the 17th of July. So that is it from me. Without further ado, I would pass over to you, Donna. Oh, Donna, you're muted, sorry.
Thanks, Will. So for today's webinar on continuous simulation modelling, it's actually going to be talk split into two parts. So first of all, both Claire and I will talk about a review report which reviews the application of continuous simulation for flood estimation. And then secondly, Paul is going to provide a practical application to the Thames Valley flood scheme. So here's the agenda for the talks. And first of all, the three of us will kick off with some introductions, and then we'll go on to those two separate parts of the talk. So I'm Donna Wilson. I'm a senior hydrologist in the National Flood Hydrology team at the Environment Agency. And I joined the Environment Agency about 3 years ago. And prior to that, I worked overseas at the Norwegian Water Resources and Energy Directorate. I've also worked in consultancy at Halcro and also in academia for a brief period. And our team's remit includes post-event analysis of recent floods, reviewing hydrology calculations for Environment Agency projects and flood risk assessments, supporting R&D into flood hydrology methods, and also being responsible for providing guidance on flood hydrology, including our flood estimation guidelines at the Environment Agency. So now I'm just going to hand over to Claire.
Hello, I'm Claire Samuel. I am Associate Director in Hydrology with Jacobs. I've been with Jacobs for over 10 years now, and I have worked in continuous simulation on and off through all my consultancy career, which I think, is getting on for nearly 25 years now. Yeah, my PhD was building stochastic rainfall models for semi-arid regions. So I've been dipping in and out of continuous simulation over those years. Most of my focus, though, unfortunately, that was probably my only overseas focus, has now been really just UK flood hydrology. So pass back to you, Donna.
Okay, thanks, Claire. We'll move on to Paul.
Hi there. So my name is Paul Boss. I work at JBA and have done for 25 years now. I got my little 25-year award the other day. And although I'm sort of the discipline lead for real-time modeling, I also do quite a lot of catchment modeling for continuous simulation, because the two things are actually really similar, or involve really similar skills. So I'll be talking to you about the sort of case study.
Thanks, Paul. Okay, so now we'll move on to talk about the review project and look first of all at why we commissioned this project. Well, at the Environment Agency, we've been finding the application of continuous simulation to Environment Agency projects has been quite inconsistent and largely perceived to be dependent on consultant expertise and preference, rather than any particular catchment characteristics or study requirements, which would justify its use. Where it has been applied, it's also unclear whether the additional time, budget, and complexity of continuous simulation has significantly increased the confidence in the results. It's also been difficult to independently verify results for quality assurance purposes. So we commissioned Jacobs to undertake a review to enable us, the Environment Agency, to make evidence-based recommendations for the use of continuous simulation. So the scope of the project is summarised in this slide, and it included looking at where and when continuous simulation has been applied in Environment Agency studies, and also looked to establish whether the hydrology is then being superseded by other methods in more recent studies, and why that decision was made, to undertake a literature review of operational applications, to identify case study examples, and also the comparison of continuous simulation outputs against the standard flood estimation handbook methods, to look at the differences there, to review academic developments in continuous simulation, also to consult with the wider hydrological community to obtain viewpoints on the perceived advantages and disadvantages of the method, to review the availability of open source and commercial software for undertaking the calculations, identify the skills that are needed for application, and also finally to recommend where and when continuous simulation modelling should be used in design flood hydrology, and also provide recommendations for any future work, future research to update the evidence, guidance, and software if appropriate. Okay, Claire, I'll hand over to you now.
A less positive slide to start with, unfortunately. So yeah, I was leading on this study, to this review, and I know some of you might have joined thinking that we were going to teach you about how to do a continuous simulation. Unfortunately, this is not what this review was about. So we do, with this presentation, does not tell you how to undertake a continuous simulation study, or recommend what software to use, or how to do it, or what the reporting requirements are, or anything like that. unfortunately. Also, the focus is on flood hydrology. I know that their continuous simulation is currently being used by our colleagues in water resources, and it's been used widely in water companies for the setting up of drought plans and water resource plans. This isn't covered here either, but well, there should be overlaps, and hopefully we can learn from them. So that's what we don't cover. But what we do cover is what continuous simulation modeling is. It gives you, hopefully we could be able to give you pointers to where to go if you want to undertake a study. We will also build on lessons learned from previous work being undertaken for the Environment Agency, as expected, strengths and limitations. The focus is also really for consultant application for practical study. That was the focus of review. And although we did look at academic papers and academic developments, and also some of the software we've looked at, there's probably more being used in an academic environment. The focus really is for consultants-led studies. So we will be able to give you some information that isn't all negative, and hopefully you should go away and learn something. So yeah, if we can go on to a brief overview of what is continuous simulation. So really, it is an alternative to the flood estimation handbook. Instead of using one idealized hydrograph, we are looking at to generate a huge multi-year process of reality to try and understand the flood risk under a whole series of events. And to do this, you need several pieces of software and huge amount of information. So really the first bit, we need to start off with a rainfall model to generate our massive duration of rainfall, usually many thousands of years. And that rainfall, that synthetic rainfall needs to be representative of or statistically similar to what's observed in the catchment. This is probably the area which is least known in consultant circles. We then move on to that output is then put through a calibrated rainfall runoff model, which as consultants we're more used to using. Again, but we need to that needs to be calibrated and need to produce observed events well. And in the simpler studies, we can stop there using those two bits of outputs, but often because continuous simulation is used in more complex studies, then we'll need a flow routing model as well to help combine all those outputs. And the one thing which is normally forgotten about, and which is really key to doing a continuous simulation, is a data management software. All this, well, we need a huge amount of observed data for the calibration process and for checking the model outputs. And also all these models generate a huge amount of data. So we need something which can manage those inputs and outputs and allow the information to be checked efficiently. There are existing, and I'll talk about them in the next slides, models, rainfall models. We know about the rainfall runoff models and things like that, but the data management software, at the moment, there is no off-the-shelf bespoke software. So that's the gap, and that's something we need to take on. Thanks, Donna. If we got ahead of me. So yes, when is continuous simulation typically considered? It's probably most well aware is when FEH is not applicable. So I think if we click again, we would come up with our standard points, which we're pretty much probably aware of when FEH isn't applicable on large catchments, when we can't assume that there's the consistent rainfall across the whole area, and complex catchments with different types of storages, whether those are man-made reservoirs or flood storage areas, or whether it's underground, it's highly permeable catchments, complex interactions from different tributaries. So yes, it's anywhere where flood estimation isn't recommended, or we cannot come up with a way to make the FEH work. So yeah, so that's when we normally consider it. So now I think I shall go through what we found out about the different types of models that are available to us. So yeah, here to start, we just first of all we talk about the rainfall models. There was a lot of good work, research work done by DEFRA in the early 2000s that was looking at rainfall models and rainfall runoff modeling as part of, I think that's the slide there, it's the FD 2105 report. I think there's also a 2106 report. And that has produced a good background, and they're great of where continuous simulation could start and has recommendations. Unfortunately, those haven't been taken forward. And the rainfall model that report does have a link to some findings and bits of software, which unfortunately the link has died, and that information is lost at the moment unless anyone else has access to it. But generally, you need a rainfall model. These are usually stochastic statistical models need to be able to generate efficiently thousands of years of data. The main ones used so far are there's GlimClim. That's an R piece of software that's been developed by Richard Chandler at UCL. If you Google, you'll be able to find that, and there's more about that in the report. Also, more recently, which isn't in the report because it was published after our report was finalised, is the RWGen rainfall model. That's a stochastic spatial temporal rainfall and weather generator. It's a development of the weather generator, which was some of you might remember from the UK CP09. So that was it's a development on that, and that's also freely available. There was a presentation given end of last year, beginning of the year. So if you do a Google search, that will probably appear somewhere, but that's available, and that is a resource which can be used and freely available. So if we now talk about, so that's the stuff as consultants we are less familiar with, and there's more pointers in the report. If we go on to the next bit, and then there's the areas which we know more about. So the rainfall runoff models and the routing models. So the rainfall runoff models, usually in the UK, PDM is used. This is sort of historically because the Environment Agency's flood forecasting models are based on use PDMs, and it's a nice place to start without having to reinvent the wheel. But we've also got pointers in the report to other models which could be used. Mostly these have been used in academic studies, but there's no reason why we as consultants and we shouldn't be using these or looking at these as alternative options. So those are points. We got pointers to those in there. And then the routing models we're probably most familiar with, sort of like Flood Modeler, with my Jacobs hat on to the Flood Modeler advertising. But these, remember, whatever you use, they need to have a quick runtime. We don't want the full hydrodynamic modeling, so these purely tend to be flow routing to try, because of the timescales we're modeling, we need to keep everything as short runtime and as efficient as possible. So if we can go on to the next bit. Okay, yes. So as part of the review, Donna kindly provided 12 environment reports of continuous simulation projects which have been carried out for the Environment Agency over probably about the last 20 years. And as expected, they were large catchments, the studies, they were highly permeable, had storage, which would be expected. There were a couple of interesting ones, though. One of them was a very small catchment, which we were looking at wanted to use continuous simulation to assess the impact of pumping. There was a pump in the catchment and understand sort of how that should be set up to manage flood risk. So that was quite interesting. And then there was another report which on an urban and permeable catchment in southeast London, which decided not to recommend continuous simulation, which was also an interesting feature. It was felt that with the additional time and cost required for a continuous simulation model, it didn't wouldn't add any additional confidence in any of the outputs, even though there'd be a more complex analysis. It didn't feel there'd be any more greater confidence in our improved understanding. And so that didn't go ahead and stuck with FEH. So that was the case when it wasn't applied. And of those 12 studies, only one of those had gone back and replaced by event hydrology. And I think that was because that was more of originally it was a catchment-wide study, and then it went become more sort of a site-specific local flood risk investigation. So that was just the one, which is good and positive to hear. Generally, at the time, GlimClim was the preferred rainfall model to use, and PDM was the rainfall runoff. And the amount, as it ranged between 1,000 and 10,000 years, the length of rainfall generated and used for the investigations. So I think the next slide is then we went out to a consultation as part of the report. We just wanted, you can put all those pointers up. As expected, I know there's lots of people interested, but it's a very small group of people in the UK. This is a specialist area, continuous simulation. I think we had about 12 or 15 respondents, but what was fantastic was everyone was positive. Everyone saw a place for continuous simulation in the application in the UK. And as expected, everyone wanted to see guidance. So we would all love to see that, to recommend how to undertake these studies. But it was felt that, and especially in a consultant environment, that lack of guidance and lack of expertise was seen as a risk to then going ahead and recommending this approach, unless it was something that the client specifically wanted. But overall, the consultation responses were greatly positive, and it was lovely to see that people did see a future in it. So if we go, so although that was some of the positives, the review did pick up quite a few limitations to the study, as expected. One thing that's just already come up is project duration and costs. They are a number of multiples greater than any flood estimation handbook style analysis. Just the amount of data and analysis required makes it a significant investment of time and cost. And as a result, there's issues with data management that's also been raised before. Those are challenges. Also, using multiple models means you're propagating errors. So you have your rainfall model, and then you're taking those outputs, doing a rainfall runoff, and then routing, and it's just understanding how those errors are propagated throughout the system. And there's also some other issues with the modelling, which can be resolved, is understanding the reliability of extremes. One of the benefits of CS is that you can look at the full range of highs and low flows, but because they're statistical models, those are unlimited, and it's like, are those really realistic and valid to be considered? And then we've also got the issues of dealing with non-stationarity and assessing climate change. Though I do know that the RWGen model was looking at developing factors to allow for different rainfall, different climate change scenarios to be included. But I'm unsure at the moment of where that is. So there are concerns about how we deal with climate change. And then my final, for just strengths, these are pretty much all the points we brought up before. Things about carrying out a continuous simulation model is that you are pretty much doing your sensitivity testing as you go. By looking at thousands of years and multiple events, you're looking at those ranges of storm durations, multiple peaks, storms happening one after another. So it is, yeah, you do get an insight, a greater insight into how to catchment response. So overall, that was it is very positive. So that is my quick whistle-stop tour through the review. And I hand back to Donna for go through the recommendations.
Thanks, Claire. Yeah, so I'm going to look at what are the recommendations then for current practice. So the review showed us that there is a consensus for the use of continuous simulation with the various strengths that have been identified. And the Environment Agency's flood estimation guidelines already provide recommendations as to when continuous simulation could be considered. And these have already been outlined by Claire. And this review found no need to fundamentally modify these recommendations, but the report does identify several considerations around data, the rainfall runoff models, and also for calibration, routing, and model runs that should be considered when selecting and applying an approach. So our flood estimation guidelines will be updated at the next update to reflect this. So there are also some future recommendations made. And so for non-standard flood estimation methods, which does include continuous simulation, at the Environment Agency, we do not provide a reporting template as we do for the FEH event hydrology reporting, as it's unlikely to be beneficial given the limited number of studies and the wide-ranging scale of the study areas and checks involved. But instead, we do currently advise that calculations need to be reported in enough detail to allow them to be reproduced by others. However, this review has identified the need to specify minimum technical requirements and a modelling checklist. And this is something that we'd like to establish at the Environment Agency, but our finite resources means that it's not something that we're actually progressing at present. There are also recommendations that were made in the report for further R&D within the hydrological community. And this includes building on those existing DEFRA research reports that Claire highlighted, and potentially establishing a consultation group to plan a way forward for the greater uptake of continuous simulation in the UK, of continuous simulation in UK flood hydrology. So then, if you haven't already seen the report is available, and you can access it by emailing my team at the Environment Agency, the Flood Hydrology team, and we can send the report out to you. Please also use the same email address if you have any feedback, questions or comments, and then we'll get back to you. Okay, thank you. I'm now going to hand over to Paul.
Thanks, Donna. Let's see if I can successfully share my screen. So I can't see anyone. So can someone just tell me, Donna, is that showing?
Yes, you're in the slide view though, so rather than just the presentation view.
Is that still the case?
It still is, yeah.
Okay, just a second. I'll just share my entire screen. That'll be easier. Okay. Is that working now?
No, we can only see you.
Goodness me. Right. View. This is what happens when you're used to Teams. I'm guessing it's still just showing presentation view, is it? Or so?
Yeah, we've got the slides down the side, but we can see the slides if you can't get it.
Yeah, okay, let's just go with that. Crikey. I guess the trouble is it's showing it on my screen, but it's obviously not showing it on yours, which is annoying. Okay, I'll share that. we'll just go with that. There is some animation on there, which is a bit annoying, but anyway. Yeah, the purpose of this bit of the presentation, or this bit of the seminar, is just to try and illustrate some of what Claire was talking about and Donna was talking about with the real world examples. So here we're going to talk about the Thames Valley flood scheme and how we've used continuous simulation to evaluate options there. And just that for this talk, the focus is much more on the methods that we've used and how we've applied them. So a bit less about the why and more about the how. And just re-emphasizing that for continuous simulation, there isn't something as strict as a flood estimation handbook that you can just pick up and apply. Instead, there's quite a bit more freedom to choose different modeling methods and how you combine them. And although that's quite good in some regards, it's also there are challenges with that as well. So TVFS, a little bit about that first of all. The Thames Valley Flood Scheme, it covers the whole of the Thames, so everything upstream of Kingston upon Thames, as shown in the map there. So it's a really large area, 10,000 square kilometres. And the project itself is looking at ways to manage flood risk at a catchment scale. So looking at wanting to mitigate risk at the sort of key hotspots, but also, right throughout the catchment. And the main way that the project plans to do that is using flood storage. So natural flood management is mentioned there, but that's not something that we investigated in detail. So what the TVFS needed was a way to be able to calculate flood frequency like everywhere in the catchment. And then to be able to translate that flood frequency curve, if you like, to what damages would occur, and therefore calculate annual average damages for the whole catchment. And then obviously the next thing would be to make our interventions, which in our case was inserting inline storage at various locations in the catchment, typically on tributaries and headwaters, and looking at how that changes the flood frequency at all those risk areas, and then allowing us to calculate a new annual average damage. And hopefully by doing that, we show that we've created some benefit, and more benefit than it would cost to actually build the things in the first place. So that's what the TVFS needs. I'm only talking about the calculating the flood frequency for all risk areas. The damages and the economics were all done by Jacobs. So I said we wouldn't talk about the why so much, more about the how, but we need to sort of address that question a little bit. And the Thames is a candidate for continuous simulation because it's complicated. So both hydrologically and hydraulically, the Thames is complicated. So hydrologically, first of all, we have basically a heterogeneous response, or a heterogeneous catchment, if you like. So we've got limestone in the headwaters that have a strong base flow component, but still respond at an event timescale. We've got clay, where we get a fastish response, but you still get a seasonal soil moisture deficit. And then we've got chalk in other areas that sort of acts like a sponge and only releases water over long time scales. And when you see what that does to a flood hydrograph, you can understand how the Thames, how floods on the Thames develop. So this shot is just showing how the response from the clay, which is the green, the limestone, which is the sort of dark orange, and the chalk, which is the Denham Coals series, they're representative of those different zones or hydrological zones. And when they combine with a very long travel time down the main Thames, you get a sort of typical Thames hydrograph as shown here. And what that basically means is that if we're interested in flood risk everywhere, like on the tributaries and on the main Thames, we've got to be able to represent the sort of flood frequency behavior, if you like, of the catchment at short and long durations, and that has important impacts for what we do with the rainfall. In terms of where the risk is, so this slide just shows us where the damages are. So the area of the circles is proportional to the damages. they're concentrated mostly in the downstream end of the Thames, like downstream of the Jubilee Channel around Staines, but they are, there's still significant damages elsewhere in the catchment. So we want to be able to calculate those damages everywhere, and one sort of benefit of working in the Thames, especially on the main reaches, is that these large hydrograph volumes mean that peak flow pretty much translates directly to a flood extent and therefore damages, which then means you can use those flood frequency curves to look up damages for different return periods and calculate the annual average damage. So I know I said I wasn't going to talk about the why, but for the reasons discussed in the previous presentation, the Thames is not a good candidate for typical design flood estimation. So at the bottom end of the catchment, you could do that by using long observed series. So you could do a sort of an FEH growth curve and calculate flood risk, or calculate flow frequency, but that wouldn't help you with inserting reservoirs upstream. And there are the sort of assumptions involved with the other options are also problematic. So that is why we ended up with continuous simulation. So Claire already explained what continuous simulation is. So I'll sort of look at more at what choices we made for how to simulate the Thames. And as Claire indicated, the sort of, if we look at the middle part of that slide, the sort of the model that's describing how rainfall is translated into flow and then routed through the catchment, that's being done by a combination of rainfall runoff models, for which we use PDM, and river models, which we use Flood Modeler. And the selection of those is really because A, familiarity, but B, the PDM is nice and flexible, is able to reproduce flows in permeable and impermeable catchments, so it can cover all of the types of hydrologies we see in the Thames. And then the Flood Modeler software is, again, very flexible, so we can do flow routing, we can dip into hydraulics if we need, and we have all the tools we need to be able to simulate the reservoirs that we intend to assess. And then on the rainfall side, it was actually during this project that RWGen was developed by David Pritchard at Newcastle University, and that proved to be a really useful development for continuous simulation as a method. And I'll say a little bit more about that in a minute. And then on the right hand side of the slide, the sort of the outputs of these, the coupling of the stochastic rainfall and the system model produce flood frequency curves, which you could then translate into damages and do the economic appraisal. Okay, so let's focus a bit more on the how. So the process of doing continuous simulation, we have to build this catchment model, which is the sort of green bit in the middle, and we have to calibrate it, but we have to validate it. And a key part of doing continuous simulation is that there are so many moving parts. It's really important to check at every point that we're getting sensible things, and not to just sort of build a model, throw a load of rainfall at it and look at the results and say that should be okay. The only way to make it work is to check everything as you go. And so on the left-hand side, we've got our setting up the rainfall model, and again, checking and, if necessary, adjusting the rainfall that comes out of that. But one of the great things about RWGen was that when we ran it, we didn't need to adjust that rainfall. We were able to use it as it is. And then when we couple those things together, we get our continuous flow series from which we can extract annual maxima, which we can just then rank and treat as, as Green-Gorton plotting position, and get our annual average, our annual exceedance probability floods out of that. But even at that point, it's important to sense check the results before we start inserting storages into some sort of baseline model and testing combinations and things like that. So I've got this little sort of index here to show us where we are in the process. So at the moment, you can see, well, hopefully the sort of, we're on the schematization and build the baseline model. And so for the Thames, the schematization involved, we needed a model that, as Claire was saying, needs to run fast, but we needed to get outputs, or we need to be able to insert flood storage areas at each of the locations where where they were potentially viable. And that tended to be on the tributaries towards the headwaters of the catchment, which dictated the sort of model's extent. But then we also needed outputs at gauges for calibration. And whenever possible, we were using existing forecasting models. And again, for speed, wherever there was hydraulic modeling, we tended to replace that with routing wherever that was manageable. So what we ended up with was 18 river models, sort of 18 separate submodels, I suppose I should call them, which are fed by 88 rainfall runoff models, PDMs, and there are 82 calibration points. So these are big numbers, and of all the continuous simulation projects I've been involved in the past, this is by far the sort of most complex and the biggest. So we ended up with also adding 17 of these flood storage opportunity areas, or FSOAs. No animation, I'm afraid, but the next sort of step, or just to illustrate how this worked, we sort of had these 18 submodels, and this is just the Upper Thames example where for each of these submodels, we calibrated it by feeding the upstream end with observed flow and calibrating both the rainfall runoff component and the routing component to make sure that it all worked well, which in this case it does, and then repeating that process for all of the 18 submodels. And then for the Thames, it was really beneficial to keep the model separate. So we maintained each of these 18 models and sort of developed them separately. And we only brought them together into one model using a script at the very end, so that we could sort of keep things manageable, essentially. And when we brought that model together and applied our observed rainfall, it enabled us to sort of just check that when everything's sort of glued together, it still produced good results. And this is the simulated flow for the biggest 8 hydrographs in the sort of 22-year period we ran the model with. And this is just using observed rainfall as an input. We're able to simulate the flow at Kingston upon Thames with, you know, a really, well, surprising to me even, degree of accuracy or precision. So that sort of builds us our sort of system model. The next step is to set up our stochastic rainfall model and run that. I am not a stochastic rainfall modeling expert, so a very simplified sort of account of how RWGen works is that it defines some storm origins in sort of over time, which are based on observations of rainfall that you give it to parameterize. And for each of those storm origins, the model sort of generates a disk that sort of provides the spatial element to which a rectangular pulse of rainfall will be applied. And that pulse has a duration and depth that is sort of defined by a statistical distribution. And when you accumulate all those, you get a rainfall series that applies to the whole catchment. We parameterized the model using 53 rain gauges and using the sort of same period of data that we used to calibrate the catchment model. And we used that to create a 5,000-year hourly simulation. And the nice thing about RWGen is that it also produces potential evaporation as part of the weather model, which means that, you know, that's another key input to the PDM. And just bottom right-hand side, just to highlight that snow melt wasn't included for us. So it wasn't seen to be beneficial to include that. Didn't think that including it would add that much value. And then this slide is just really, this is just nice to illustrate what the rainfall model actually produces. So we took a chunk of the rain simulation and made a little animation out of it just because we were curious to know what it actually looked like, because normally you're just dealing with massive files full of data. But it's good to see that the rainfall generator produces things that look like rainfall, although that's not really a sort of an endorsement of the model. It's nice to see that it actually works, and it was helpful for the Environment Agency and reviewers to see that happening. The important checks that we did do with the rainfall was to get the depth, duration and frequency statistics out of it at various points and compare that to FEH. And in general, we saw some differences. So what we're showing in this table is a color shaded comparison. So if the numbers are red, it means that they're lower than the FEH 22, and if they're blue, they're higher. So at this location in the catchment, we're a bit under. But if I step down, we've got another location in the catchment where we're a bit over, and we had others where you're pretty much bang on. But overall, that looked good enough to be able to take forward into our sort of simulation modeling. So once we've got our model of the catchment and our stochastic rainfall and our potential evaporation, I guess this is where people start to have questions about, well, how does it actually work beyond that point? What are the mechanics of it? So what we needed to do was to run the rainfall runoff part continuously, because they account for antecedent conditions and soil moisture conditions. So those were run continuously for 5,000 years to produce a flow series that are going to form the boundaries to the routing models. But at the same time, we also identified some lumped PDMs that were representative of different parts of the catchment. And we used those, again, run continuously to identify potentially large events. So anything more than QMed, actually. And by sort of identifying those events or the dates of those events, we were able to amalgamate those into periods for which we would run the sort of river part of the model or the flood model part of the model. And so what we ended up having to run for the Thames was around 35% of the 5,000 years. So we saved on having to run 65% by throwing away the dry years and the sort of less significant flows. Once we've sort of coupled everything together and run it for that period, we were able to extract the annual maxima and compare that to observations at different gauges. There was a further step of sort of streamlining, whereby we took a 1,000 year chunk out of the 5,000 years, the one that was most representative of the 5,000. So this plot, the sort of dark purple line that goes on a bit longer than the others, is the 5,000 year simulation at Kingston upon Thames. And then these other lines are the individual 1,000 year chunks. And we tried to pick one of those that was representative as possible everywhere and use that in our scenario testing. Another sense check was just to look at the hydrographs at different locations. So this is just the sort of biggest 8 at Kingston upon Thames. And just glancing at it, if you know that sort of part of the Thames, the hydrographs look reasonably sensible. So there are some sort of single peaked events like the number 3, but then there's events like the number 8 and the number 7 that are combined of multiple, accumulations of different rainfall events. And then I guess the moment of truth is when you've done all that simulating and you compare the flood frequency coming out of the continuous simulation in purple with observed annual maxima that are plotted on the same sort of flood frequency curve. And what we saw was that we were getting a good match at lower order events and generally matching the sort of the pattern that we could see in the observed AMAX. There were some differences with the sort of flood frequency curves that had come from previous analysis, and particularly on the Thames, that is steeper because it tends to follow the NRFA annual maxima. But we're also matching pretty well on some of the, on most of the tributaries, but I'm only showing you a couple of those. So there's the Mole and the Wey that we're matching the sort of steeper flood frequency on those. So at that point, I think that's a significant achievement that we've produced this model or this tool that's able to reproduce the baseline observed flow frequency everywhere and give us a way to robustly appraise the storage options. And we don't really have time to go into this, so I've just got one slide just to show you the kinds of things we did. So we inserted all of these flood storage areas checked that they didn't make any difference when they were neutral, and then started playing around with pass-forward flows. And more recently, we've even been trying active storage to see what benefit that can have. And just out of interest, at Staines, which is our sort of most significant risk area, even with all of the storages active, we're achieving an 11% reduction with everything, all guns blazing, as it were. Okay, so just to finish off and share my reflections on this particular continuous simulation study, the first reaction was that it worked, and it wasn't a sort of a certainty at the start to sort of do this kind of study. And I think both us as the consultant and the reviewers and the client were really happy with the outcomes, and it seemed to give a lot more confidence to the appraisal of these different storage options. Another thing related to actually doing the work is that being transparent and communicating regularly exactly what you're doing and what assumptions you're making and sharing results was really important. And it felt like a team effort between ourselves, Jacobs, the reviewers, and the Environment Agency. And although it's really hard to envisage an alternative way of doing this sort of study for the Thames, but as Claire mentioned, you really do need specific modelling skills, and this particular study, because it was so massive, has required a significant time input. And as Claire also mentioned, that software to sort of coordinate the whole process is like another sort of barrier to entry, if you like, in terms of doing that. But on the positives, the RWGen rainfall generator has been a big step forward and has worked really well for the Thames. Okay, thank you very much. I'll just stop sharing.
Brilliant. Thanks to all the presenters. I found that really interesting. While we wait for questions to come in on the chat, I actually have a quick question, if that's okay. I think really for everyone. So when not that I've dabbled much in it, but when I've worked with continuous simulation in the past, particularly applying economic appraisal, one challenge we came across was, when you're using FEH, you have these, quite understandably, quite standardized hydrographs with often quite comparable durations and profiles. But obviously for economics, you need a range of different return periods. So when the challenge we had with selecting return periods is that actually, although according to annual maxima and according to peak flow, the peak flow may be fairly linear in terms of the annual maxima, the profiles between those events and the durations can be quite different. And particularly when you're doing catchment hydraulics, you can have these receptors in a catchment that are particularly sensitive to duration or particularly sensitive to peak flow, and that can cause what we found was that can cause some non-linearities in the distribution of damages between different events. I wondered if that's something anyone's come across, or if there's any thoughts on that at all.
Well, in this particular case, we were looking at relating damages to the flood frequencies directly. So we just made an assumption that for most of the Thames, the water level in the Thames or the flow in the Thames was representative of the damage. So you didn't have to worry about just partial filling of risk areas, which is reasonable for that case. But I don't think I've come across that before at a catchment level, but I'm typically more involved in the flood frequency calculation than the economic damages calculation. But sort of the cool thing about continuous simulation is that those sort of assumptions about which event caused what return period at what location, as long as everything is being simulated, you don't have to make assumptions about that. You can just use the data straight out of the model, as long as it's got the processes in it that are dictating what's at risk.
Yeah, brilliant. Thank you. And I think really from it was a methodology issue that we were facing in the past as well. So by no means want to down talk continuous simulation. So yeah, sorry, that's it from me. Kirsty, are you happy to run through the questions that come in?
Yes, thank you. Sorry, I just got booted out actually, so I've lost access to the chat history, but I think I saw a question about how the flood storage areas were modelled.
So yeah, sorry, was that the question about how the flood storage areas were modelled? Yes.
Yes, that's right.
Yeah, so they were modelled very simply, just as reservoirs with a boundary downstream that sort of described what would be like a break structure and a spillway for overtopping. So they were really simple.
Okay, thank you, Paul.
Do you have the questions, Kirsty? Do you want me?
The next one I can see is from Ben Gibson, unless there was one before that.
There are some before that.
Okay, yes, please could you fill them? Sorry.
That's fine. That's fine.
Thank you.
So we've got a question from I guess Keith Bevan. In normal FFQ analysis, results depend a lot on tails of chosen distributions. In CS, that is transferred largely to tails of rainfall generator, including the possibility of some very large events in long synthetic series. How did you deal with this on the Thames study?
So we didn't intervene in the outputs of the stochastic rainfall generator. So what we did do was we used RWGen to give us the stochastic rainfall series, and then checked essentially that it produced the depths that we would expect at the different durations with the same sort of frequency that Flood Estimation Handbook predicts. So I think the answer is we dealt with it by checking against Flood Estimation Handbook depths, and we also tried as far as possible to check the performance of the catchment model with the longest observed annual maxima that we had. So there's definitely an acknowledgement on our side that the whole thing was only reproducing what was actually sort of embedded within the model. So if the catchment were to respond in a very different way in some future event, for example, say the chalk all froze one year and you got heavy rainfall, that's not in our continuous simulation. So that's certainly a limitation. But everything else was dealt with by checking.
Brilliant. Thanks for that answer. Kirsty, I've just got one more before you're caught up, and that is the methodology used to provide the point at which peak flows would be reached?
Well, it does provide for every event that it simulates. It does give you a point at which peak flows would be reached. So the easiest way to think about it is for continuous simulation is as if you had observed the sort of river levels or flows at every point within the catchment for 5,000 years. That's essentially what it's giving you, although they're clearly not observations, but all of the sort of richness of those data can be sort of leveraged or utilized. And I think that the tough thing that some people struggle with continuous simulation is that the design event on one reach or tributary will be completely different to the design event on another reach. So if you're looking for the 100-year flow, it will be a really different event that gives you that on one of the Thames tributaries compared to the main stem of the Thames.
Brilliant. Okay, Kirsty.
Oh,
Thanks.
Thank you. Yeah, thanks, that Will. So the next question is from Ben Gibson. In such a large system, can continuous simulation address the predicted impacts of climate change, which may vary spatially and for different durations?
Thanks, Ben. That is a difficult question. So what we're basically saying is, can I guess, can the meteorological inputs to continuous simulation, does a model like RWGen or RainSim, is it able to reproduce that? And the answer is yes, if you've got the data to train it on. So if we didn't know how rainfall was going to change in future, we could train a model like RWGen to do that. And again, I'm not like an expert on stochastic rainfall generators, but there are parameters that you can adjust that would sort of change the behavior of the model to be more like some future scenario. So I think the general idea at the moment is that you would look at how those parameters change, looking against outputs from climate change models to see how you should change the parameterization to give you visualizations or realizations of future scenarios.
Thanks, Paul. Next question / comment is from Tim Hunt, wondering if there is scope in the future to produce national stochastic datasets that could be used and reduce the time to develop catchment models. There's something similar in coastal modelling.
Yeah, that's a really good point, and I don't see any reason why that's not possible with some of these big hourly data sets. So the first time we ran, the first iteration of our modelling, we used Newcastle University's 2009 web generator, which was perfectly capable of producing a stochastic data set for anywhere in the country. That could be done. There might be quite a bit of checking required to make sure it was matching FEH depth, duration and frequency, but yeah, it's a good idea.
Yeah, and just to say, I understand that with water resources, they do have sets of simulations, sort of which they use, which are available for anyone to use. So those have been set up for water resources and low flows for water companies. So I don't see there's any reason why you couldn't do that for the high flows, or just generally for everyone, really, if you want to get completely comprehensive.
Great, thank you both. The next question, is there any movement in the individual synthetic rainfall pulses as per Railstorm, or is it uniformly dumped across a single area? Just thinking about the ability to capture routing / timing of plausible events.
Yeah, so the simple answer is no. The rain cells don't move; they just develop over an area and then decay. So that is something that's missing from the rainfall model. There's no advection.
Okay, and I think this will be the last question that I can see in the chat. So as it was mentioned that you will require very fast models for this approach, how long did it take you to simulate thousands of years? And then a follow on, and were the model running on sub-daily time steps?
Yeah, so the models were running sub-daily. I think our save interval was every 15 minutes. And so for a 1,000 year simulation, using multiple processors, I think we were using about 6 or 7 processors. We could do that in about 9 hours, one simulation. And we did hundreds of those. So.
Thank you. Sorry, I have just noticed one last one that I missed. Did you have any difficulty in fitting the RWGen model parameters across the 53 station records that you used? And that's a question from David Cross.
We didn't have any difficulty fitting them. Based on our sort of comparison of the depth, duration, frequencies coming out of the model at the end, with FEH sort of 22 statistics, they all seem to line up reasonably well, plus or minus 20%. So we think that the sort of fitting process seemed to work across the multiple stations.
Great. Thank you, Paul. And Claire and Donna, I think that's all the questions that I can see in the chat. So thank you everybody for the questions that you've asked there. Will, I'll just hand back over to you.
Yep, brilliant. Thanks, Kirsty. My video. Oh, there we go. Yeah, so there is just one final comment from Sam Bray, just to add to Tim's query from the reassurance catastrophe modeling world, some of the CAP modeling vendors do have national stochastic rainfall time series for up to 50k years, though not at the same resolution Paul has shown. So that's not a question, just a final comment there. Brilliant. Again, yeah, thanks to the speakers. Thanks for answering all of those questions. Just another final plug for the BHS National Symposium. I'm pasting a link in the chat now. Once again, this video will be up on our YouTube channel in the imminent future, so do keep an eye out for that. Thanks again and enjoy the rest of your day. Brilliant. There's some people hanging on, but I think we can call it there.